Let us have some old concept of phase velocity and group velocity. So Vp equal to omega by beta. Beta is the phase coefficient. Vp is the phase velocity. Omega is the frequency, angular frequency. So omega by beta will give you the phase velocity. But actually phase velocity doesn't have any real significance. The actual energy is propagated through the with the help of group velocity, Vg equal to delta omega by delta beta. Okay, so beta can be written as n1 into k, that is n1 into 2 pi by lambda. So n1 into omega by c. So Vp equal to c by n1. So if we using this particular relation, Vg equal to d lambda d beta into d omega by d lambda. Okay, so it is d omega by d beta. We are writing it in this way, that d lambda by d beta into d omega by d lambda, right? So d lambda of this one beta, and this one will give you the minus omega by lambda. So ultimately we are getting this relation Vg equal to c by n1 minus lambda into dn1 by d lambda. So this term, this particular term is written as ng. So basically Vg equal to c by ng. Okay, where ng is called the group index of the guide. Okay, so actually the energy of the electromagnetic wave or the light wave will be propagated with this particular velocity, which is governed by this ng. Okay, and generally this ng is not equal to n1 because we have another term dn1 d lambda. Okay, and most of the cases this is not exactly zero, right? This is not exactly zero. So ng will be different from n1, and obviously Vg will be different, right? Depending on the nature of the fiber. So this ng is also a very important parameter for optical fiber. Now for cylindrical fiber, we have just shown that we have the uh, wave equation in cylindrical domain, in cylindrical coordinate system, and we can solve it, right? So we can rewrite this wave equation in this way, okay, where beta phase velocity, phase coefficient can be written as n to k, which is less than n to k, but greater than n to k, but less than n1k. So psi can be written in this way. Okay, we are not going into the details of those calculation, mind it. We don't require to calculate it again. Okay, the calculations are there. We will just use those relationship according to our need. Okay, so from the solution of electromagnetic wave inside the cylindrical optical fiber, we can determine two parameters u and w. Okay, the normalized frequency is a dimensionless parameter and hence is also sometimes simply called the v number. So using this u and v, we can determine, u and w, we can determine a parameter called the normalized frequency, that is u square plus w square whole to the power half. So from these two expression we can determine this we just replacing this u and v, u and w, and finally we get the expression for v as 2 pi by lambda into a into na, numerical aperture, and we know the expression for numerical aperture. So 2 pi by lambda into a n1 into 2 into delta whole to the power half. Delta is the index difference. Okay, also we have normalized propagation coefficient b. This is another parameter, and that we can also derive using this u and w, and this is the expression. Okay, so we have two important parameters. One is the v, another is the b, this one. Okay, we now consider different type of fibers. The first of all we will consider step index fiber. Step index means the core index, obviously it is constant N1, and cladding index is N2, and it is suddenly changing the refractive index. The refractive index is changing suddenly at the interface. So this type of fiber is called the step index. That means the index profile will produce a step function like this one. Okay. Now the diameter of this core may be larger, diameter of this core may be smaller. Okay, depending on the application. When the diameter of the core is larger, the incident wave may fall inside the uh, core region at different angle, right? They are falling at different angles. Okay, but when the core dia is small enough, it is very it is not possible to have such different angles of the incident rays. So ray will follow almost straight path. Okay, so as you can see, when the diameter is larger, we have different waves to propagate, and for each kind of wave we have different electric field profile. Okay, that means we have different modes to be present inside the optical fiber. That means this type of fiber will allow different modes to propagate. But when the code dia is very small, like this one, the fiber will not allow the wave to propagate with different modes. It will allow only a particular mode to propagate, right? So when the diameter becomes larger, different modes will be available inside the fiber, and such fibers are called multi-mode fiber. But when the code dia is very small, of the order of few micrometer only, then it will support only one mode, the minimum mode, and that particular fiber is called the single mode fiber. Okay, now here we have shown some irregularities, like fiber may have some disturbances like this one. So under that condition, uh, it may change the angle. Okay, that means suppose the fiber, we have launched the ray inside the fiber with an angle of phi 1 in such a way that the incident angle should be phi 1, but due to this irregularity, the reflected ray, it should have a same angle of phi 1, but because of this irregularity, it may have phi 2 angle, right? And it will be supported if we have multimode fiber. That means the original mode was this one, but it may generate this mode, right? Not only that, whenever we have some bending, fiber bending, then because of this bending, the angle may change. Okay, like this one, angle may change. So that will also, it is also possible that because of the bending, different modes may be generated for this one, right? But as per single mode fiber is concerned, we don't have this type of problem. Okay, now let us try to understand the step index fiber in little bit in details. A multi-mode step index fiber with a code dia of around 50 micrometer or greater, which is larger enough to allow the propagation of many modes within the fiber core. 50 micrometer core means it is of the order of diameter of human hair, right? So it is very thin. Even then, we are saying it. as a larger core. Okay. The single mode or monomode step index fiber, which allows the propagation of only one transverse electromagnetic mode, that is HE11, and hence the code dia must be of the order of 2 to 10 micrometer only. The single mode step index fiber has the distinct advantage of how intermodal dispersion. We will discuss this type of dispersion later on. So it is basically the broadening of transmitted light pulses as only one mode is transmitted, whereas with multimode step index fiber, considerable dispersion may occur due to the differing group velocities of the propagating modes. Each mode will have different velocities because the incident angles are different, right? So higher the mode, higher will be the incident angle, so larger will be the path length, right? So in that way, the single pulse may be divided into smaller mode and higher modes. So smaller mode will appear earlier and higher modes will appear later. That will produce a pulse broadening. That is called the dispersion. Well, this in turn restricts the maximum bandwidth attainable with multimode step index fibers, especially when compared with single mode fibers. However, for lower bandwidth application, multimode fibers have several advantages over single mode fibers. The first of all, the use of spatially incoherent optical sources, which is nothing but the light emitting diodes or LEDs, which cannot be efficiently coupled to single mode fibers because of various reasons. Actually, these light emitting diodes, uh, the the area through which the light is emitted through this light emitting diode is quite larger. Okay, and since the single mode fiber has a very tiny core dia, so obviously it is difficult to couple the light emitting diode with the single mode fiber. Okay, so for light emitting diode, large core area, multimode fibers are more suitable than the single mode fiber. For single mode fiber, we have to use the laser because laser will emit the light with very uh, so it is a very small spot size, which is easier to couple with the single mode fiber. The larger numerical aperture as well as core diameters facilitating easier coupling to optical sources. Lower tolerance requirements for fiber connectors because for lower bandwidth application we don't want to mm, the expenditure that we want to mm, that we want is we must reduce the amount of expenditure, right, to have a low bandwidth application. So that for that the low cost multimode fiber is suitable compared to single mode fiber. Single mode fiber is very costly. Consider one numerical problem. A multimode step index fiber with a core dia of 80 micrometer and a relative index difference of 1.5% is operating at a wavelength of 0.85 micrometer. If the core refractive index is 1.48, estimate the normalized frequency for the fiber, number of guided modes. So V number, normalized frequency means V number. So V number is approximately 2 pi by lambda a n1 into square root of 2 delta. All the values are given. So we will get 75.8. 75.8 is the V number. And number of modes can be estimated as approximately V square by 2. So V is already determined and number of modes that the fiber will support is uh, nearly 1800, 2800. That means 2873 number of modes are supported.